Welcome again to electrostatic field. This time we are with boundary valued problems. More specifically, we'll discuss parallel plate capacitance. Here we are with a fast revisit for solution flow, where we start with Laplace equation. We use the boundary condition, then we determine basically the voltage. After that, we use the relation between voltage and electric field to determine E equal to minus grade of V. Finally, before calculation of the capacitance, here we calculate the charge density, and from it we calculate the charge. Then using the charge and the voltage, we calculate the capacitance. In this specific problem, we are asked about the parallel plate capacitance. So let's read it together. We have two infinite perfect conducting plates, this one and the one bottom in the bottom. And this here z equal to 0, z equal to d. Here we have a voltage V naught. Here we have a ground. And between them, there is a dielectric which has epsilon as a permittivity, and this is d and this is 0, then the thickness or the distance between the lower and upper plate is d. And we are being asked step by step, first calculation of the potential, which is the voltage, and the electric field distribution between the two plates, surface charge density, and finally the capacitance per unit area between the two plates. As we discussed, to solve such a problem, we need to write Laplace equation. So Laplace square V equal to 0. And since we have a perpendicular in the z direction and we don't have any variation in xy directions, then we can use this fact to cancel these two components. We don't have any change here. As we know, if this one is, these two plates are conductors, so field will be perpendicular to this plate, and this direction, this n is k, and this n here is minus k. So that's why we cancel these two components. Now we are left with partial square v by partial z square equals 0. Then we can rewrite the equation here, make a one-time integration. Then here we have 0. This will result in a constant. One more integration, a become az, and we need to put a constant. So at the end, we will have v equal to some constant a multiplied by z and some constant p. Here we come to the second step, which is applying the boundary conditions. We have V naught in the upper plate, we have 0 in the lower plate. This means at Z equals 0, we have V equals 0, and at Z equal D, we have V equal V naught. So let's start with Z equals 0. We have V equals 0, and applying this equation, when Z equals 0, then the total here will be 0. This means we are left with B is equal to 0, this one. The second step, to go to the other plate where Z equal to D, we have V equal to V naught, which is applying again in here in this equation. We have A multiplied by D by replacement of Z equal D. And of course, from the previous one, we got B equal 0. So now we can calculate A by dividing both sides by D. Then A will reduce to V naught over D. So we can conclude that the equation which we derived here is simply V equal V naught Z divided by D. Now we move to the calculation of the electric field, which is possible by applying the gradient relation with the electric field, E equal to minus gradient of V. And from the previous slide, we have the relation between V and the dimension, V equal to V naught. And the important thing here is Z over D. V naught and D are just constants. These are just constants. Then when we apply the gradient relation, which is here for your memory, and since this one is only a function of Z here, then these two components will be 0. Then you will be left with this component only. So substitute here, considering only the last component here. Then you have minus, this is from the original equation of the gradient relation with electric field. Then k, which is the direction here. Then differentiate partial by partial z of what? Of the function, this function, which is v naught z over d. Derivative of z is just 1 and v naught over d is just a constant. Then we can say that E is nothing but v naught over d in the direction of k. Then we go to the charge density, and this is possible. Let's plot this again. We know that this is normal here. Normal here is k. Normal here is minus k. If we know the electric field at any point, just multiply by the normal and don't forget to multiply by epsilon, then you can get the charge density. And this is what we are doing. Electric field, we already proved here or here, just minus v naught over d in the direction of k. This is just the electric field multiplied by the normal, which is minus k. And finally, don't forget to multiply by epsilon. Then simplify, you can get the value of rho s at the top plate. And we know that if this was a positive value, then here we will just have the negative value. So and don't forget that this is because they have the same area. If we are in different problem, it may be a little bit different. So anyway, since these two plates have the same area, if we plot remind each other, this has A, and then also this should have A as area. So in that case, just multiply by negative sign what you calculated here, then you can get the value of the charge density for the lower plate or the bottom plate. Finally, the final thing is the calculation of the capacitance, which is possible by dividing. Normally, we need to divide C equal to Q over V, but since we are being asked to calculate the capacitance per unit area equal to rho S over V. And here V is just the voltage difference between the upper and lower plate. So if this was V naught and this one is already zero, the voltage difference here V naught minus zero, which is just V naught. That's why we substituted this V naught here. Divide the charge density, which calculated here, by the voltage. Then finally you can get capacitance per unit area equal to epsilon over d. And if in the previous video, we proved that the parabolic capacitance is equal to epsilon over d multiplied by a. So it is the same result because this is capacitance per unit area and this one is the total capacitance. Thank you.